sum of AMN, AMK star, AMK, GNO. Then you can say the another condition is the ensemble average or expectation. Now, these two quantum conditions can be applied to all the ensembles, all the three ensembles. Let us first consider microcanonical ensemble. What we have told in microcanonical ensemble, we have two ergodic surfaces where the energy varies between E to E. Energy E varies between E minus delta E by 2 by E minus half delta E and E plus half delta E. And within that surface, we say by the statistical principle equal a priori probability method, we can write the density matrix in the form of your 9 equation rho mn is rho n delta mn. And you have already told the diagonal of diagonal elements rho n is 1 by omega for each accessible state. When states are accessible, this is 1 by omega, that is thermodynamic potential, which is correlated to our entropy, that is S is equal to K log N, K log omega. And the rho n, the density matrix rho n is equal to 0 for all other states. Remember, rho n is 1 by omega for all accessible states. And it is equal to 0, okay, it is 0 for all other states. And now we will consider one example, that can we calculate entropy. When we calculate entropy, will Gibbs paradox arise in quantum mechanical ensembles, which was true in classical mechanics? The second question is, what is the physical significance of those quantum states? When we consider S is K ln omega, when you consider omega is equal to 1, then you will find S is equal to K log 1. So there is only one diagonal element rho n which is equal to unit. And the density matrix satisfies the condition rho square is equal to rho. What is our density matrix? Density matrix is represented as rho mn, which is 1 by n times summation k is equal to 1 to n amk ank, which is amal, and rho mn square is nothing but rho m into rho n. Rho m, you can say rho ml into rho lm. These are two matrices, and product of these two matrices suggests rho mn square is equal to rho mn. Hence, we have studied the behavior, the physical significance of the density matrix, as well as we suggest the entropy calculations are possible without any Gibbs paradox. And the equal a priori probability which evokes this one, this suggests the amplitude part. I mean, we have considered the wave function psi m as ak by amk phi m. So the psi to phi is carried by a matrix, and that matrix satisfies equal a priori probability, and that is in the form of this one given in equation this, that is rho mn is 1 by n times amk star, which is 1 by n summation k is 1 to n mod a square e to the power I theta mk minus theta nk. And in terms, we can take this normalization factor and other amplitude square factor as a constant, and this becomes C delta mn. What is C? C is a constant in microcanonical ensemble. So this contradicts the expected result was contradicted in microcanonical ensemble as expected in classical physics. Now we can note the second postulate which arises in quantum mechanics. and it indicates that this deviation or the absence of the correlation between members of various systems can be uprighted, can be made corrected in canonical ensemble. So what was the difficulty? Out of the two definitions of quantum mechanical result of ensemble theory, we find the second postulate is being contradicted, is not obeyed in case of this microcanonical ensemble. So we considered the canonical ensemble. What happens in canonical ensemble? We have TVN remains constant and energy becomes a variable one. Remember, in canonical ensemble, number of particles remain constant, volume remains constant, temperature remains constant, but energy varies. So we can since energy varies, we can randomly choose the probability function, and the density matrix takes the shape that rho mn should be equal to rho n delta mn. And what is rho n? We have derived rho n in our microcanonical ensemble, that is C e to the power minus beta en, and n varies 0, 1 to any integer, any real number. So the constant we define here, a quantum mechanical partition function of the canonical ensemble, that is Qn through C. We have defined rho n as C expectation minus beta En. What is constant C? Rho n is this C expectation minus beta En n factorial. But rho En is this factor C is 1 by sum over n e to the power minus beta n, which is 1 by Qn beta. This factor, which is related to C, this Qn beta, is called partition function for canonical ensemble. Yesterday we have defined Z as class partition function for canonical ensemble in classical statistical mechanics. In quantum statistical mechanics, what is the difference? We define Qn as partition function for quantum mechanical canonical ensemble, which is related to a constant C, and the constant C is nothing but 1 by sum over n number of system of particles by systems e to the power minus beta En. Why it is possible? Because energy is variable 1. So the density operator or the density matrix by consideration of this partition function takes the shape this one, that is rho is equal to, this is ket phi n. I have defined in quantum mechanics, instead of wave function we can write this is ket phi n, this is bra phi n, and this is ket phi n 1 by Qn beta e to the power minus beta En. Remember, you have 1 by Qn beta is this one, this factor, and this is e to the power minus beta n. So you can say these two, this energy factor gives rise to 1 by Qn beta, and this is ket, this is bra of it acting on e to the power minus Ben gives rise to e to the power minus Bh, and this is the factor phi n. And you have read the completeness theorem in quantum mechanics. What does it indicate? Ket phi n and the bra phi n summation gives rise to, or can be defined by a physical quantity which satisfies your second quantum mechanical result by assumption for ensembles, that is the expectation of Gn is the trace of expectation of Gn or average ensemble average for n particles, the physical quantity G is the trace of rho G, which is equal to 1 by the partition function Qn beta into trace of G e to the power minus beta h, which is the trace of G e to the power minus beta h by e to the power this one. You can find in this equation, we have told you that G must have, this is the expression, G must be trace of rho G by trace of rho. The same thing is chosen here. G in canonical ensemble, we satisfy this equation, Gn is equal to trace of rho G in equation 9.24, which is 1 by Qn beta trace of G e to the power minus beta h, which is the trace of G divided by this one. So it satisfies the second mechanical condition. Hence, we can suggest for a fixed n. For fixed n means fixed number of systems or fixed number of particles. This satisfies the second quantum mechanical assumption, which was not satisfied by microcanonical ensemble. Then for more specific result, we can consider the grand canonical ensemble. And we can apply the quantum mechanical operator, that is your density operator, by way of quantum mechanics. So what will be the density matrix or density operator for grand canonical ensemble? That will be, for grand canonical ensemble, this will be rho, this factor rho 1 by Q0, which is a function of mu Vt. I have told you mu is the chemical potential, and in grand canonical ensemble, mu Tv remains constant. Number of particles and energy, they are variable factors. Chemical potential, volume and temperature remain constant in the grand canonical ensemble. Hence, the density function, you can see the density function is your rho operator, density operator is 1 by Q0, Qg we have considered. Qg means grand canonical partition function. Here partition function canonical ensemble was only Q. Qg function of mu Vt e to the power minus beta h minus mu n. Yesterday we have defined this one, and the Q mu Vt will be summation, this will be plus factor e to the power beta er minus mu ns. Because in grand canonical partition function, we consider both the reservoir and the system. That's why R and S, R represents for reservoir and S represents for our systems. So this is e to the power minus beta er minus mu ns, which is the trace of e to the power minus beta h minus mu n. The ensemble average G, now we can calculate if this is the partition function, grand canonical partition function, Qg mu Vt is e to the power minus beta er minus mu this one, then grand canonical partition function is 1 by Q0 mu Vt into trace of G e to the power minus beta h e to the power beta mu h, which is summation n is 0 to infinity z to the power n average of Gn Qn beta divided by this one. What is z? Z is e to the power beta mu, and this factor z here e to the power beta mu, yesterday we have told this is fugacity of a system, and this fugacity of the system determines how the ensemble average in a canonical ensemble is correlated to the grand canonical partition function. And what is the physical significance of fugacity? Now it correlates, it makes a correlation between canonical ensemble average and grand canonical ensemble average. So in order to know these three applications, we will consider a free particle in a box. We all know we have solved the problem of a particle inside a box in our quantum mechanics. What happens? We have calculated the energy, we have considered a cubical box, then a free particle means its potential energy is 0. So consider a box, cubical box, and each side is L. So Hamiltonian is given by the equation minus h cross square by 2m L square plus V psi, V is here 0. So this will be simple minus h cross square by 2m del square. H, and the operator Hamiltonian will be h cap is equal to minus h cross square 2m del square. Then minus h, that will be in 3 dimension, minus h cross square by 2m del square by del x square plus del square by del y square plus del square by del z square. Now, when you apply the periodic boundary condition, this is at one end of the cube. On the other end at the L, so x shifts to x plus L, y shifts to y plus L, and z changes to z plus L on the other end. So the periodical boundary condition suggests that phi, if phi is the wave function, phi was initially a function of x, y, z. Now phi x plus L, y, z must be equal to phi x, y plus L, z, which is equal to phi, which is a function of x, y, z plus L, which is phi x, y, z. That means they satisfy the periodical boundary conditions or periodic functions. So we define a wave function phi e which can satisfy this above Schrodinger's equation for a free particle, that is phi e t, phi e, which is a function of, you can say, which is a function of t, or you can say f in your book, is 1 by L to the power 3 by 2 e to the power ikr. Let this is the wave function, and this arises due to length factor or normalization factor, such that the wave vector k is represented as kxx cap, ayy cap, and kzz cap. When you put the values of k in the wave function and you apply the boundary condition, you will derive the expression for or eigenvalue energy equation. What is the eigenvalue energy equation? That will be h cross square k by 2m. This is the energy. And what is the wave vector for k? You have read k is equal to kx, ky, kz is a function of this one along 3 directions. That will be 2 pi by L, nx into ny into nz. Or you can say simply k is equal to 2 pi L into L. And now our aim is to calculate the density matrix of a free particle. So how can we find density matrix of a free particle for a canonical ensemble? Now that is, you can say that is, you have a bra r e to the power minus beta h into k r dash. Or you can say that is ensemble average of e to the power minus beta h in coordinate space. So that can be written as the ensemble average of r e to the power minus beta e and e r dash, which is equal to e to the power minus beta e and expressed by your function, that is phi er and phi star er. So when we made some mathematical simplifications, you will arrive the result that the trace of e to the power minus bx is equal to your some factor v multiplied by m divided by 2 pi beta h cross square whole to the power 3 by 2. So this indicates the Hamiltonian of the particle is related with the mass of the particle. That was the conclusion. Not only mass, it also depends on beta and the volume of the cube inside which the free particle propagates. And now in this unit we can conclude that we can apply the Hamiltonian equation or Schrodinger's equation, that is H when acts on a wave function, it denotes IH cross del by del T and psi k such that IH cross del by del T is the energy operator value or Hamiltonian operator value which can be applied to statistical mechanics. And the second conclusion is the wave vector psi kt has the form a n t phi n, and corresponding a n kt can be written as phi n star psi kt dt or d tau. And we also found the amplitude factor a n mod square is equal to 1. We define density matrix rho mn as 1 by n ANKT, and under equilibrium condition, rho is equal to rho h and del h by del t is 0. Then we define the dynamical variable g, which was already told that is 1 by n sum over q is 1 to n, an star, ank, gnm, and g is equal to trace of rho g divided by trace of rho. So finally, we define the average dynamical variable and we calculate the grand partition function. Now, in the next unit, we will discuss about the different types of statistics. We have already read your Maxwell-Boltzmann statistics, which were classical one. Now we will focus another two types of statistics which deals with bosons and fermions. If it deals with bosons, this is Bose-Einstein statistics. If we deal with fermions, this is Fermi-Dirac statistics. So we will define those bosons and fermions. Then we will have a focus after Bose-Einstein statistics. We have a focus on Planck's radiation law because it gives vital information on the spin half particles. The bosons are integral spin particles and the spin half particles are fermions. So, considering only you will find in Maxwell's function there is a factor called 0 epsilon, and when it is positive you will find this is Fermi-Dirac statistics, when it is negative you will find that is Bose-Einstein statistics. And while discussing Bose-Einstein statistics, we will calculate the thermodynamic probability, the most probably distribution state, and the Bose-Einstein distribution function. Similarly, in Fermi-Dirac statistics, we will calculate the probability, thermodynamic probability, the most probably distribution function, and the Fermi-Dirac distribution function. Besides, we will define here the Fermi energy, which is differentiate for very particles like which are conductors, which are semiconductors, and which are insulators. Then we have a comparison between three types of statistics: Maxwell-Boltzmann statistics, our Bose-Einstein statistics, and Fermi-Dirac statistics. So the first is what is quantum statistics and what is the symmetry principle in quantum mechanics. In quantum mechanics, I have told the fermions as well as the bosons plays an important role. So to distinguish themselves, we must know what is symmetry. What is symmetry in quantum mechanics and how it is applied to the statistical mechanics. Let us consider large number of interacting particles. when you consider large number of identical, indistinguishable particles, automatically those particles lies at different positions, say R1, R2, R3. So how can we define state of a function? The state of a function is represented by means of its positions, psi of R1, R2 and R3. Hence, this psi of R1, R2, R3 can be written as, we can write this wave function as psi of plus psi of R1, R2, R3, then we say this is symmetric function, symmetric wave function. If psi of R1, R2, R3 is equal to minus psi of R1, R2, R3, this is called antisymmetric function. Antisymmetric function. So we find if psi is equal to psi of R1, R2, R3 is plus of psi of this is symmetric function. If it is minus of this one, this is antisymmetric function. Now we have bosons and fermions. So these two are essential to note. Properties of bosons and fermions. Bosons, what is their spin angular momentum? 0, h, 2h, 3h, so on, h cross, 2h cross, 3h cross. What is fermions? That means they are integral spins. Fermions are spins half h cross, 3 by 2h cross, 5 by 2 means half integral spins. And bosons does not obey Pauli exclusion principle. Remember, you have read Pauli exclusion principle in chemistry, Pauli and also atomic physics. Bosons do not obey Pauli exclusion principle, while the fermions obey Pauli exclusion principle. Then the wave function for bosons are symmetric in nature, and the wave function of fermions are antisymmetric. That is, psi is equal to plus psi, symmetric for bosons, and psi is equal to minus psi, that is antisymmetric for fermions. What are bosons? Some examples of bosons.
What are bosons and fermions? We have to.
Hello.
What are bosons and fermions?
Bosons. Okay. Bosons and fermions are particles, quantum mechanical particles. Photons, protons, phonons, deuterons, mesons, they are included as your bosons. What are fermions? Electrons. All spin half particles. All spin electrons, positrons, neutrons, protons, muons, pions, okay, mu plus, mu minus, they are treated as fermions, and because they are antisymmetric in nature. And the photons, they are photons, phonons, they are bosonic particles, or they satisfy Bose-Einstein condensation. Besides that, they do not satisfy Pauli exclusion principle, and they are symmetric. Here, while in spin half particles, which are our half integral spin particles, they are electrons, positrons, neutrons, protons, and muons. Now, this is the basic idea. The Bose-Einstein statistics purely deals with the bosons. So, what is the postulates of Bose-Einstein statistics? These are two important parts. Always, you have questions in statistical mechanics. You will find questions from Bose-Einstein statistics as well as Fermi-Dirac statistics. So, first postulate of Bose-Einstein statistics: particles are identical. When particles are identical, they are indistinguishable. We cannot distinguish between different particles because they are similar. First postulate. Second, bosons obey Heisenberg uncertainty principle, that is delta x into delta p is greater than equal to h cross by 2. And bosons do not obey Pauli exclusion principle. Third one is, in case of bosons, there are different eigenlabels. So they can, since they have different eigenvalues or eigenlabels, they have different quantum states. And there is no restriction for bosons to occupy different quantum states. That is most vital point. Once, due to third postulate, different eigenstates or eigenvalues or eigenlabels, they occupy different quantum states. There is no restriction on it. Suppose I will choose one quantum state, say ith quantum state, and in ith quantum state, I have Ni number of particles. Then what is Ni number of particles? Then sum over Ni must be equal to total number of particles minus is equal to n, which is Ni, sum over Ni is equal to n, which is equal to total number of particles. Because a particle can stay in different states. They have different eigenvalues. So if n is constant, Ni is constant, what is their variation? Summation delta Ni, it will be automatically 0. So when summation Ni is equal to 0, so the total energy becomes constant. When total energy is constant, change in energy, that is delta U, is equal to 0. Now we can suggest, if delta Ni is 0 and delta U is equal to 0, what does it physically signify? In quantum mechanics, we have discussed the all quantum states have equal a priori probability. All quantum states are probable, that is equal a priori probability. So we define a number Gi, we define a quantity Gi whose energy is Ei, and in this state, Ni are indistinguishable particles, and there is no restriction on this. So so we can calculate what are the number of quantum states. That will be Gi plus Ni. In this picture, if Gi represents these gases and Ni represents the dots. Okay, gases represents Gi and the dots represents Ni. Suppose Ni are 4, 0, 2, 5, 2, 1, then there is no restrictions in the other side. So we can say Gi plus Ni quantum states are possible. Here quantum states 4 plus 2, 6 plus 5, 11 plus 2, 13, this is 14, 3, so 17. So next here states are, here we have 8 states, 4, 6, this is 5, this is 2, this is 1, this is 3. So you have 8 states initially, and there are 17 Ni states. So Gi is 8 and Ni is 17. So total number of states is Gi plus Ni, that is, these number of states are possible. And these states, can we know thermodynamic probability? In first class we have discussed the quantum mechanical thermodynamic probability, any thermodynamic probability is defined by Ni number of particles in Gi number of states. So thermodynamic probability omega I is Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. This is the equation. This equation was defined in first class. And the omega thermodynamic probability is the sum over the total number of particles, that is Wi. And omega is summation Ni plus Gi minus 1 factorial by Ni factorial into Gi minus 1 factorial. This is the most probably distribution, and this is most probably distribution of Bose-Einstein distribution. When we consider Bose-Einstein distribution, remember we have to assume two things. Ni is much greater than 1 and Gi is much greater than 1. Then we will apply Stirling's approximation to this equation of probability, which was Ni Gi minus 1. Remember, this is Ni plus Gi minus 1, Ni factorial Gi minus 1. When this is much greater than 1, so this 1 is neglected. Then in the numerator, you have Ni plus Gi factorial. In the denominator, you have Ni factorial multiplied by Gi factorial. Then you apply Stirling's approximation. What is Stirling's approximation? Now log n factorial is n log n minus n. You apply this factor 2, then a log of omega. You take log of this factor omega. Log of omega is log of Ni plus Gi factorial minus ln n factor Ni factorial minus Gi factorial. Then you proceed. Finally, you will find under equilibrium condition, this logarithm of this factor del of log omega, B means Bose-Einstein statistics thermodynamical probability factor. This B is equal to 0. And delta log B is 0 means this suggests in equilibrium condition, two quantum mechanical results we have derived, that is delta Ni is equal to 0 and energy delta E is equal to 0 are satisfied. So we have satisfied these two equations for equilibrium. If you consider delta Ln, this is omega is Bose-Einstein thermodynamic partition function probability, then this is delta Ni log Ni plus Gi minus log Ni, which is equal to minus summation log Ni by Gi plus Ni into delta Ni. For equilibrium, you can write log of Ni by Ni plus Gi into delta Ni is 0. And delta Ni is equal to 0 indicates delta sum over I epsilon I into Ni must be equal to 0, or epsilon I into delta Ni is equal to 0. This indicates delta Ni is 0. When you have a product epsilon I delta Ni is equal to 0, this epsilon I is a invariant quantity. And if you calculate by, you apply Lagrange's method of undetermined multipliers. You choose a constant lambda or here say alpha and beta. So we can define this equation by Lagrange's method of the constants, by Lagrange's method of undetermined multipliers. And what are the multipliers? Alpha and beta. You add delta Ni, this factor, delta Ni.
Your screen is not visible.
Okay, delta
Okay, we have books.
delta Ni log delta Ni log log of this factor, log del omega B must be equal to 0, which indicates summation epsilon I delta Ni is equal to 0, and in turn what you obtain, now this log of delta Ni are arbitrary, for which these two constants alpha and beta, which are your Lagrange's undetermined multipliers, are expressed in terms of this one, that is log of Ni by Gi plus Ni minus this is 0, or a log of 1 plus Gi by Ni is alpha plus beta epsilon I, and What is 1 plus gi? That will be e to the power alpha plus beta epsilon I, and this is what is gi by ni is 1 by 1 plus this one. Sorry, 1 plus this one, and ni by gi is this. This is called your Bose-Einstein distribution law. Remember, once again, in equation 10.12, we have defined Bose-Einstein distribution law, that is function of epsilon I is ni divided by gi, which is 1 by e to the power alpha into e to the power beta epsilon I minus 1. You will find in Fermi-Dirac statistics this minus 1 will be plus 1, and you have found in your Maxwell-Boltzmann statistics that ni by gi is only 1 by e to the power alpha into e to the power beta epsilon yesterday. And now you consider gi is much greater than ni. This is Fermi-Dirac distribution function or distribution law. F of epsilon I is ni gi, which is 1 by e to the power alpha into e to the power beta epsilon I minus 1. So you apply Stirling's approximation, that is log n factorial is n log n minus n. This will be log gi factorial minus log ni factorial minus alpha minus beta epsilon I 0. Hence we rewrite this equation, if f of epsilon I, this equation, ni by gi, which is 1 by e to the power alpha, e to the power beta epsilon I minus 1, can be rewritten as e to the power alpha 1 by e to the power beta epsilon minus 1 can be written as e to the power minus alpha e to the power minus beta, because this 1 is neglected. And what is beta? Beta is 1 by k beta t. This is your Maxwell-Boltzmann distribution function. Question asks, derive an expression for Bose-Einstein distribution function. Derive an expression for Bose-Einstein distribution function and show how it varies, how it is different from Maxwell-Boltzmann distribution function. You will say this 1 is not there. This factor is 0 in Maxwell-Boltzmann distribution function. Now we will focus on Planck's radiation law. We all know in radiation, in the topic of radiation, we all read that for black body, Kirchhoff's law suggested that there is a conservation of energy. So conservation of energy means when some amount of energy is absorbed on a black body, the ratio of emissive power to absorptive power is equal to the ratio of emissive power to absorptive power of a black body. Ratio of emissive power to absorptive power of a body is equal to ratio of emissive power to absorptive power of a black body. That is E lambda by A lambda is equal to E lambda. But that was not true. Then it was modified by Stephens, who suggested the emissivity of a body is directly proportional to fourth power of absolute temperature. E is equal to sigma T to the power 4. That is true for black body only. But for any other body that was not true. Then your Stefan-Boltzmann law came into picture. It was modified by Boltzmann, and Boltzmann suggested E is not equal to sigma T4, rather it is sigma T to the power 4 minus T0 to the power 4, where it is true for any body where T0 is equal to absolute temperature. But when you studied the wavelength versus your energy density graph, E lambda D lambda graph, we suggested the energy distribution considering the Stefan's law into account was randomly populated. That's why wind displacement law came into picture. Wien suggested the wavelength corresponding to maximum intensity is inversely proportional to absolute temperature. But this law is only true for lower wavelength region. Hence, this law was not taken into consideration. Then Rayleigh modified it on the basis of statistical mechanics. Rayleigh suggested that the gas molecules can compare as the systems. In number of particles of a system, molecules can be treated as particles of a thermodynamic system or statistical system. Then what he did this thing, he applied the statistical mechanics principle to explain black body radiation and gave Rayleigh-Jeans formula, and James suggested that it is only true for
Hi, friends. Carry on the call.
is it audible now? Uh-huh.
Yes, sir. Yes.
Rayleigh-Jeans formula was only true for higher wavelength region. It is not true for lower wavelength region. So Planck's radiation law came, and this is true for both lower wavelength and higher wavelength region. It is suggested that each atom can be treated as a oscillator, and each oscillator is associated with an energy h nu, and if each we divide large number of systems, and some have energy 0, and a number of particles having n0 having 0 energy, n1 number of particles having h nu energy or epsilon energy, and n2 number of particles having 2 epsilon or 2 h nu energy, and so on. So you take the average of energy and you calculate the energy density within the frequency range, then that will be u nu d nu or u lambda d lambda. So you can find the equation of your book 10.16 that u nu d nu, or you can express in terms of u lambda d lambda. U nu d nu is 8 pi nu square by c square h nu by e to the power h nu by k beta t minus 1 into d nu. What is nu? Nu is c by lambda. You can convert, take it u lambda d lambda form. Only d nu will be minus c by lambda square d lambda, and nu place will be c by lambda. Hence, you apply this one, the total energy you can find, the number of particles having this one, NEDE, can be written as GE divided by e to the power alpha, the number of particles or number of photons whose energy, one photon has energy h nu. So this energy, number of particles having energy E, and within, lying within the ergodic surface E and E plus D becomes GE divided by e to the power alpha into e to the power e by k0t minus 1 into dE. You apply this to quantum momentum range. When you apply not in energy range but in the form of momentum range, so NED was replaced to the quantum mechanical momentum range P to P plus delta P as GP dP is 8 pi Vp square by dP. You can find this equation. This is the number of particles, and this is Gp, P is 8 pi Vp square by h cross q into dP, equation 10.18. So this gives rise to the total number of quantum states. When you apply the statistical mechanics to Planck's law, then total number of states, quantum states G nu d nu is 85V, this one 85V p square by h cross q. P, instead of p we have used this term h nu by c. For energy we have used h nu, and change in momentum was replaced by h by c into d nu, h by c into d nu. So above equation becomes this equation, which was earlier defined G nu d nu. GPdP is converted to G nu d nu, and it becomes 8 by V by CQ nu square d nu. For an assembly of photons inside a cavity in a heat reservoir at temperature T, the assumed photons are continually emitted and absorbed by the wall of the container. What does it indicate? This indicates that delta Ni, change in number of particles, is equal to 0. That means the number of particles are not conserved, which means this equation does not hold. That means number of particles delta Ni should be 0, but here Ni is not conserved, so delta Ni is not equal to 0. So what is the number of particles? Now you can suggest the number of particles n nu d nu in equation 10.22 is G nu d nu divided by e to the power h nu by k beta t minus 1. If you combine this equation n nu d nu and you combine the equation this one G nu d nu, these two equations, G nu d nu was 85V by CQ nu square d nu, and you combine this equation n nu d nu is G nu d nu by this one. You put the value of G nu d nu here, then you obtain n nu d nu in equation 23 is 85V by CQ nu square by e to the power h nu by k beta t minus 1 into d nu. Since the energy of the photon of frequency nu is h nu, the energy per unit volume of the enclosure, the energy density U nu d nu becomes h nu by V n nu d nu. And U nu d nu, after simplification, gives Planck's radiation law 8 by h by CQ nu q by d nu divided by h nu by k beta t minus 1. So we are able to calculate the Planck's distribution law considering the photon theory into account, and photon is nothing but a boson. So one example of Bose-Einstein statistics is calculated considering photon, which is a boson that satisfies by quantum statistical mechanics principle. It satisfies the Planck's law, and Planck's law are derived. Next we will focus on Fermi-Dirac statistics. Fermi-Dirac statistics, what are the basic postulate? I have told fermions are spin-half particles. So the particles are identical, hence indistinguishable, first postulate. Second one, it obeys Heisenberg uncertainty principle as well as Pauli exclusion principle. Bosons do not obey Pauli exclusion principle, but here fermions obey Pauli exclusion principle as well as your Heisenberg's principle. Then the state would remain in empty state, or they can contain one fermion. Here we assume the quantum mechanical state are defined by prior restriction on occupancy. There cannot be simultaneously more than one particle in one quantum state. Remember, in Bose-Einstein statistics it was different. Here we cannot have the more number of particles in one quantum state. So delta Ni is equal to 0 and delta Ui is equal to 0. When you consider the Fermi-Dirac statistics, we consider the number of particles, say, which are distributed among the fermions, n1 number of particles having energy level epsilon 1, N2 particles having energy level epsilon 2 and so on, Nn particles having epsilon n. Then we consider the thermodynamic probability. Here for fermions we take probability as Wi, thermodynamic probability for fermions, which is the Gi factorial by Ni factorial minus Gi minus Ni factorial. Then you calculate for total number of particles, W is equal to sum over Wi, that is omega Fermi-Dirac. Fermi Bose-Einstein रे B लिखिथिला, this omega Fd, this is the Gi factorial by Ni into Gi minus Ni factorial. So when you calculate the most probable Fermi-Dirac distribution, this most probably is log of omega Fd is log Gi factorial log Ni factorial minus log Gi minus Ni factorial. You apply Stirling's approximation and you will obtain this result that delta of log omega Fermi-Dirac is minus delta Ni into log Ni minus log Gi minus Ni, which is log Ni by Gi minus Ni delta Ni. So log of this Ni by Gi minus Ni into delta Ni is equal to 0, and Ni is equal to Gi by e to the power beta epsilon divided by e to the power alpha plus beta epsilon plus 1. I have told you, you got Fermi-Dirac distribution function f epsilon I 1 by e to the power alpha e to the power epsilon I divided by k beta t plus 1. देखो only difference between Bose-Einstein statistics and Fermi-Dirac statistics is there is minus 1 in Bose-Einstein distribution, but it is plus 1 here. So number of particles having energy epsilon and d epsilon is g epsilon d epsilon divided by e to the power alpha e to the power alpha epsilon I by k beta t plus 1. Here n epsilon d represent number of particles having energy between epsilon and epsilon plus d epsilon. So we have a quantity alpha minus epsilon f by k beta t, and if you apply this factor, then the Fermi-Dirac distribution, this is final function 1 by e to the power epsilon f minus epsilon f minus epsilon I minus epsilon f by k beta t plus 1. This is Fermi-Dirac distribution function true for fermions. Let us define what is Fermi energy. I have told you that Fermi-Dirac distribution function for a state energy, ith state energy, ith level energy, epsilon I is less than epsilon f. When energy of ith state is less than Fermi energy, then Fermi-Dirac distribution function has value 1, and it is 0 if it is greater than Fermi energy level. So we can have this picture. This is Fermi-Dirac function, distribution function. This is a term T is 0 degree. T is 0 here, 0 degree Kelvin. This is your Fermi energy. Epsilon f stands for Fermi energy. This is Fermi-Dirac function. This is 0. This is half. Where this distribution decreases. Fermi-Dirac distribution decreases in this manner. This is your Fermi function, and this is your Fermi energy. Now you can say what is the physical interpretation of Fermi energy. Now this energy represents the probability occupation at t is greater than 0, which means 50% of the quantum states are occupied and next 50% are empty. That means in case of, suppose example, physical example, in case of conductors, you have fixed valency band, but your conduction band is empty. And when the mobility of the electrons increases, the mobility of fermions increases, they cross the Fermi energy band and moves to the next higher band. That is the Fermi state. So for different temperature, these are the plots of 10.2 and 10.3, which indicates that the temperature range is different, as a result of which the Fermi energy state becomes different. Then we have focus on ideal quantum states, where we define an occupation number ns. This occupation number is 1 by e to the power beta epsilon s plus mu plus k, and this occupation number n epsilon in the macroscopic level for continuous distribution function takes this shape 1 by e to the power beta epsilon minus mu plus k. What is mu? Mu is the chemical potential, that is minus alpha times k beta t. As a result, in quantum mechanics, the number of quantum states can be expressed in terms of occupation number. So, the variation within the number of particles in the phase space, that means phase space means dq r dqp or dq q dqp by h cross is dqr dqp volume element by h cross q multiplied by the occupation number ne. This can also defined by a number g. If you define by number g, this is g into dqr dqp by h cross q into n epsilon. And in this manner, when you calculate, you arrive a constant factor dn is equal to cv e to epsilon to the power half d epsilon by e to the power beta epsilon mu plus k. This c stands for 2 pi 2m to the power 3 by 2 by h q g. This is a constant. So this indicates that this dn by d epsilon is proportional to the exponential factor. That means the number of particles as a function of energy non-relativistic quantum gas is proportional to epsilon to the power half. So dn by d epsilon is e to the power minus beta epsilon. For these are expression for non-relativistic fermions. This is number of particles having energy epsilon versus energy. This is dn by d epsilon versus epsilon graph, and n stands for your occupation number. This is at low temperature, for low temperature, and B stands for high temperature gases. Now occupation number and distribution function n epsilon and distribution function graphs are given in this manner. So when you calculate this one, the total energy of the system comes around Cv e to the power epsilon to the power 3 by 2 d epsilon divided by e to the power minus beta epsilon minus mu bracket plus k. Hence, if you calculate in this manner, you can define the fermions that the function f of zeta, f of or zeta of mu t, the function is treated as zeta of mu t is equal to Cv n epsilon mod square epsilon to the power d epsilon. This is the corrected form of occupation number, and it increases when particle density is higher. So the range of energy where the occupation number is large, this equation is obeyed. Now we will focus on weakly degenerate systems and strongly degenerate systems. A system is said to be weakly generated if in this equation ये जो expression हमें देखिले n रो expression for n, if n is equal to Cv epsilon to the power half d epsilon by 1 by a, this one, if a is this factor a is very less, then we say less than 1, much lesser than 1, this is called weakly degenerated system. If it is much greater than 1, then this is strongly degenerated system. And for weakly degenerated system, the A0 value, which is called fugacity of the system, quantum system, A0 is fugacity of a quantum system, is given by n Cv k beta t to the power 3 by 2 into t to the power 3 by 2. So the fugacity which is correlated with the temperature, you can calculate in terms of gamma function, and finally you got the result. A0 is 1 by G H divided by V by N to the power 1 by 3 2 pi mk beta T to the power 3 by 2. And this equation explains how electron conduction takes place in metals. I have told you that the conduction, for conduction, good conductors, there are 10 to the power 23 number of atoms in one volume, and there are 10 to the power 23 free electrons which are responsible for the conduction in electricity. And this is true for your weakly generated system. When you consider strongly degenerate Fermi systems, the A value is large and the occupation number, this A factor is much larger. The N is equal to occupation number 1 by A to the power minus 1. This A is very large. If A is less weakly degenerate system, and for such systems, you calculate that the occupation number for various state tends to 1 and A tends to infinity. When the system is completely degenerate, this occupation number for Fermi-Dirac statistics is 1 by e to the power epsilon s minus mu whole divided by k beta T plus 1. And when you deal macroscopic system, this is 1 by e to the power epsilon. Instead of epsilon s for systems, this is for total reservoir and system, epsilon minus q by k beta T plus 1. So you can find this is a plot of occupation number versus which is a function of energy. This is how they vary. This is your Fermi energy versus your occupation, Fermi-Dirac statistics occupation number. And you have different energy levels and different states are depicted in the picture. So you have various metals here in your table 10.2, that is lithium. It gives an energy this and its temperature. This is Fermi energy and this is Fermi temperature of various metals are given. And depending on that, we can calculate that which metal has a higher number of electrons and which metal are capable. Higher number of electrons means lower energy is required. That is the work function of the metal. With less amount of energy, we can dislodge the electrons from the surface of the metal. So now we have a comparison between Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac distribution function. I have told if Ni by Gi is equal to F 1 by e to the power epsilon minus mu by k beta T plus k. If this k is 0, this is Maxwell-Boltzmann statistics. If k is plus 1, this is Fermi-Dirac statistics. If k is minus 1, this is called Bose-Einstein statistics. Then what does it indicate? What does it differentiates? It differentiates that we can have from the same formula we can derive it. How? Now, if you consider a Bose-Einstein method, if you take the indistinguishable particles in Bose-Einstein statistics, then you have considered the Pauli exclusion principle is not applied there. But you can calculate the same by applying Pauli exclusion principle in Fermi-Dirac statistics. Only difference is in the function you have a difference part 1. Now we will move to unit 11, that is application of Fermi and Bose statistics. The first one is we will discuss the strongly degenerated systems. We have already told for strongly degenerated systems the temperature is less than Fermi temperature, much less than Fermi temperature, then they are strongly degenerated systems. and the mean occupation number is represented as CV. We have read there K beta T to the power 3 by 2 into integration 0 to infinity of a particular value. So when you put that value, you will calculate an expression for chemical potential which is given in your 11.4, that is mu T chemical potential expression. This is Fermi energy multiplied by 1 minus pi square by 12 T by TF square plus pi to the power 4 by 80 and so on. What does it indicate? The chemical potential depends on the Fermi temperature. So for space in each case, we have considered a term while considering N, that is CV, that is called electronic heat capacity. So how this is related? We know total internal energy of a system is equal to, if N is total number of occupation number, average occupation number, if epsilon is average energy, then E is equal to NE. This E can be written as in equation 11.5, that is CV K beta T to the power 5 by 2, where X is into X to the power 3 by 2 dx, E to the power X minus X0 plus 1. Our X value is epsilon by K beta T, X0 is mu by K beta. So you apply Sommerfield's lemma, then you calculate. Finally, you will arrive this result. The energy is 3 by 5 N epsilon F 1 plus 5 pi square by 12 T minus TF square minus pi 4 by 16 T by TF to the power 4 plus higher orders. So this plot indicates the internal energy for strongly degenerated systems. For classical gas, it was a straight line passing through the origin. But for strongly degenerated systems, the ideal Fermi gas, the graph between internal energy and temperature starts from a little from the your Fermi energy point, and it moves. Finally, it touches at Fermi temperature. So the conclusion of this graph indicates that the heat capacity can be written as CV for a monoatomic gas or Fermion systems. CV is del E by del T, and it comes around pi square by 2 NKB by TF into T. So we can calculate for these systems, we can calculate the heat capacity and heat capacity for fermions. We have calculated heat particles for molecules of a gas in thermodynamics, but here we are able to calculate for fermions, electron heat capacity can be calculated. So depending on the applications, we have read how the temperature of the resistor or temperature of the conductors, insulators, violates the motion of the molecules in not only conductors, but that violates that also defines the superconducting behavior or electronic behavior, electrons behavior in superconductors. And now when you find a graph, you take CV is equal to alpha T plus beta T square, you plot a graph CV by NK beta T. This is the temperature variation of constant value heat capacity of an ideal Fermi gas. You will find the variation is not in this manner, rather it took in this manner. This is the variation plot of CV, which indicates that we can calculate a factor at known as entropy S, which is nothing but integration 0 to T CV by T into dt. So if you perform this integration by putting CV, you will obtain this is the value of entropy. So entropy of strongly degenerate Fermi-Dirac gas becomes 0 when T is 0. Remember, when T is equal to 0, S is entropy which is proportional to T and related to TF, that is Fermi temperature. When T tends to 0, S tends to 0. That means Fermi-Dirac gas drops to zero at absolute temperature. That is the most important conclusion. Then in your 11.3, we have to discuss thermoionic emission. Thermoionic means thermo plus ionic means heat. Heat energy is capable to derive electrons for metals whose work function is low. When thermionic energy or a metal is heated, the thermionic energy, if becomes greater than the work function of that metal, then the electrons are dislodged from the surface of the metal. This phenomenon is called thermionic emission. And for thermionic emission, what are the conditions? The emitting surface must be plane one, and the energy must be greater than work function, that is epsilon, given in your 11.16 equation, px square by 2m is equal to ec, work function of the metal. Then the electrons are evolved from the surface. In television sets, in cathode ray oscilloscopes, and in other processes, you will find by hitting the metal surface, electrons are generated, and those electrons moves forward, strikes luminance surface, and they are capable to produce glow. So these are the applications of statistical mechanics, as a result of which we are obtaining some modern devices. Then there is an equation: when the electrons flow, there is a current density. It is related to your temperature. Depending on the temperature, the current density changes, and it was initially given by Richardson, but later it was corrected by Dussmann. Initially it was a T-half formula, that the current density I is equal to A T to the power half e to the power minus beta T, where beta is equal to 1 by K beta T. But now the Richardson's formula, Dussmann formula, suggested it is not proportional to T square, it is proportional to T to the power half, it is proportional to T square. So how can we start? We consider thermodynamic current per unit area, then we integrate over the momentum axis, we integrate it over the volume components, momentum component and volume component. Finally, we derived an equation which is given on your equation 11.24, that is J, that is thermionic current density is A T square e to the power minus beta or epsilon by K beta T. So thermionic current density is directly proportional to square of the temperature. This indicates that the electrons, free electrons in a metal, are dependent on the temperature. The more the temperature, the more will be the kinetic energy, and when the kinetic energy is greater than work function of the metal, at that time we can extract the electrons from this one. So this is the Richardson's equation. And besides that, these gases, Fermi gases, the free electrons which are compared as Fermi gases, which are treated as Fermi gases. In 1927, Pauli suggested that the conduction electrons, especially in alkali metals, are treated as highly degenerate Fermi gases, and their behavior, they shows magnetic behavior. They are weakly attracted, so they are called paramagnetic substances. And we know paramagnetic substances, the susceptibility is inversely proportional to temperature. So this behavior is studied by Pauli and suggested the Pauli paramagnetic principle in case of your fermions or Fermi gas. So Pauli suggested that in presence of an external magnetic field B, the energy is given by epsilon, that is P square by 2m, minus mu star B. You can see in equation 11.21. If xylem is, this is kinetic energy part of the electron. Mu star is the intrinsic magnetic moment of mass m, and B is your external magnetic field, which is anti-parallel. Here mu star and B, they are anti-parallel vectors. When mu star is anti-parallel to B, your energy epsilon is minus p square by 2m plus mu star B. When it is parallel, this minus sign is replaced by a plus sign. Remember, when mu star and B are anti-parallel, then it is plus sign. When it is parallel, epsilon is p square by 2m minus mu star B. So, depending on the spin, we consider the occupation index or the occupation energy, number of particles occupied in the energy level is represented by N. We earlier know that is 4 pi V by 3 HQ 2m epsilon F plus mu star beta to the power 3 by 2. Occupation number of two groups. This is for one group and this is for other group particles. One is for plus parallel. Parallel is for anti-parallel we have plus sign, and for parallel we have minus sign. So the magnetic behavior when studied by these two equations, and we calculate the susceptibility. The susceptibility takes these two values in 11.29 and 30 equation. Susceptibility becomes 3 by 2 n mu star square by epsilon f, and another susceptibility at infinity is n mu star square by k beta t. And finally, when you plot a graph, Pauli exclusion paramagnetism graph between the total energy of the electron with magnetic moment parallel and anti-parallel, this is, you will plot this graph. E is taken along y-axis. This is the magnetic moment parallel spin. This is for anti-parallel. Right side is for anti-parallel, left side is for parallel spin. You will find how these variations takes place. This is the energy axis. This is under magnetic field applied parallel. This is magnetic moment applied anti-parallel. This is the plot of parallel plot. This is for anti-parallel plot. And this represents the Fermi energy level, the total Fermi energy level at 0 degree. All the levels up to Fermi energy are occupied. So you can calculate in this case the number of particles that represents in here one shaded portion, this one, your own shaded portion. Okay, these two indicates that the magnetic field are either how the magnetic moment affects the number of electrons position, or number of electron position becomes different, how mu and B are anti-parallel and parallel. So we can conclude that there is a Pauli paramagnetic susceptibility which indicates there exists in the magnetic behavior of ideal gases, and it is not strong, it is weak, so we assume them, we treat them as paramagnetic substances. And due to conduction of electrons, there is a current, and the surrounding the current, we know there is a change in magnetic field when there is a motion of electron. And because of Pauli exclusion principle, the electrons have an energy. As a result, due to that energy, the magnetic field gets changed due to spatial motion of electrons. So these are the three conclusions. Then for strongly coupled systems, we will find the same thing. Same thing happens. That is for Bose-Einstein leads to Bose-Einstein condensation. Strongly coupled systems. So we will consider some particles of a system which are distributed in excited state. The electrons are not in a normal state, they are in excited states, and the number of particles in the excited state is related with some constant multiplied by 2 pi mk beta t by h cross square to the power half. This is given in your equation 11.40. In excited state, the number of particles is n excited, that is 2.612 some number multiplied by v into volume into 2 pi mk beta t by h cross square. So what is Bose-Einstein condensation? Now, in 1925, they suggested a number of molecules are steadily growing with increasing density over the first quantum state. That first quantum state means kinetic energy is zero, while the remaining molecules are distributed themselves, and the separation between them, the gap between them creates a conduction path, and at that point the separation region is called saturated ideal gas region, and the condensation occurs there. So the number of occupants is given by 11.42, that is n is equal to n excited state 2.612 v 2 pi mk beta Tc. Tc is known as Bose-Einstein condensation temperature by h cross square. That means after condensation, some particles moves to the higher value, and Bose-Einstein condensation indicates the following two phases. The particles are possible to occupy or distributed among different excited states. When a gaseous phase contains n excited particles and distributed over excited state, then their energy epsilon must be greater than 0 and rho I must be greater than 0. When condensed phase consists of number of particles minus excited particles, that means the particles concentrated with energy, then in first case epsilon is greater than 0. In this case epsilon is equal to 0 is equal to minus pi. And in this case you will calculate the number of particles in the excited state is the total number of particles into T is the temperature divided by condensation temperature to the power Bose-Einstein condensation temperature to the power 3 by 2. So this is a plot of different distribution of bosons as a function of temperature below and above Bose-Einstein condensation temperature. This one is the bosons. This is the temperature and this is your distribution function of bosons. This is a plot. This is below condensation temperature and this is above condensation temperature. And these are the number of excited particles when T is greater than Tc. This is excited when T is less than Tc. So the phenomenon of Bose-Einstein condensation can be summarized as follows. First one, when T is equal to 0, the bosons condense. Remember, when T is equal to 0, the bosons condense into the lower energy state. As T increases, the number of particles in the ground state decreases. When temperature increases, the number of particles in the ground state decreases. When T is greater than Tc, the particles are in excited state. That means when temperature is greater than your Fermi temperature, then you can suggest the particles are in excited state. So due to this excited state, the conduction of electrons depends on Fermi energy. And Bose-Einstein condensation plays a major role in defining the electron flow as regards to the Bose-Einstein condensation is considered. So in this unit, we consider the number of various principles of condensation, and our next unit we will deal with the imperfect gases and the virial equation. Yesterday we will also discuss the Kamerlingh-Onnes equation, which you have read Kamerlingh-Onnes equation in superconductors, and we will discuss. The first thing is we will discuss what is an imperfect gas. We know for imperfect gas, we know an equation, the density is equal to rho of k beta T, and to satisfy that equation, we will discuss the quantum virial theorem. In order to discuss quantum virial theorem, we consider a collection of molecules of a system. We define a scalar product G is equal to sum over I, sum over all the particles of the system, which is evoluting with the time. So this is rho I dot into Ri dot. Then when G has time evolution property in 12.2, we can write dG by dt, we can differentiate. This is summation I rho I dot Ri with respect to time derivative plus Ri dot into rho I, where these are dependent, time dependent. I stands for ith particle, MAI is mass of ith particle. Now, if you calculate the total energy is kinetic, that is half of sum over I MAI VI square. So the dG by dt becomes 2 times kinetic energy, and that is equal to plus a factor sum over Fi Ri. So the time average of dG by dt in the time interval 0 to tau can be written as average of this is 1 by tau integration 0 to t dG by dt into dt, which is 2t times t is your kinetic energy sum over I Fi Ri. When you evaluate this integral, you come across that 2t is equal to this factor, integration higher limit to lower limit, and it gives the t expectation is minus half sum over I Fi Ri. So this is called virial calculus or virial of calculus. This is known as virial theorem. And the RHS factor minus half summation I Fi Ri is called virial calculation. This equation is used to derive Boyle's law. You can derive Boyle's law by using this equation, and our next discussion will be the Kamerlingh-Onnes equation. Kamerlingh-Onnes equation, which suggests that the Kamerlingh-Onnes equation expresses the deviation of perfect equation of state in form of an infinite power series of rho. So we have this equation P by K beta T is rho plus B2T into rho square plus B3T into this one. Here B1, B2, B3, these are called virial coefficients. So first three virial coefficients are functions of temperature. They are all function of temperature and independent of density and pressure. So we can rewrite this equation as P by rho K beta T, you take rho common here, is B2T rho plus B2T rho square. So when you move to the second term and third term, you will find that the virial coefficients are obtained in terms of interaction between ith number of molecule in a volume V. Hence, we can arrive by considering this, we can say what is physical statement, what is the physical significance of this virial coefficient. In order to study that, you have to consider the grand partition function. The grand partition function, this is a function written in terms of sum, which is function of v, t and mu, grand partition function. You can take any function of this type. This is an inverted m in horizontal manner, or w you can say. This is function, and this is qn nvt e to the power mu n by k beta, which is summation qn nvt lambda to the power n. What is lambda? Lambda is equal to e to the power beta mu, and beta is 1 by k beta t, and mu is chemical potential, that is 1 by n total energy plus PV pressure, volume, T is temperature, and S is internal energy. So when n is equal to 0, the energy becomes 0, that is single state. And the grand canonical partition function becomes 1 plus summation qn. Qn is partition function for qn, which is a function of PV into lambda to the power n. Qn stands for function of canonical function, and this is grand canonical function. They are related with each other by means of this virial theorem. And the average molecules is given in 12.19, that is n is equal to k beta t del log ln. This is some grand canonical partition function, which is differentiated with respect to the chemical potential mu, is equal to lambda times del by del lambda of log grand canonical function at when volume and temperature remains constant. You know that density and pressure here does not change. Density and pressure remain constant in grand partition function. So by considering that the partition function z, for our convenience we can say when z tends to rho and rho tends to 0, at that time the grand canonical partition function becomes 1 plus qn v to the power n by q1 to the power n into z to the power n. Now Zn is equal to m v by q1 to the power n into qn. This is called partition function, in which is partition function, which can be rewritten in this manner. Then for interacting gases, we will discuss first three virial coefficients using grand canonical partition function. We have given virial coefficients B1, B2, B3. We will consider that by considering these virial theorems. First three virial coefficients. We know the density function rho, which is the number of particles per unit volume, that is lambda by v. What is the n? N in the previous unit is the del of log of grand canonical partition function by del lambda. In turn, it gives z by k beta t del rho by del z into vt. Z is the canonical partition function. So we have, if we proceed this manner, then z can be written as a1 rho plus a2 rho square plus a3 rho q and so on. And by putting this, if you solve this equation, you will obtain three of your virial coefficients. Three virial coefficients by using Grand Canyon, that is A1 is 1, value of first virial coefficient. The second virial coefficient A2 is minus 2B2. Third one is A3 is minus 3B2 plus 8B2 square. We also can prove this result. Prove A1 is 1, A2 is equal to this. This is given in some examples. Then we will focus on second virial coefficient. We will focus on second virial coefficient, that is your second virial coefficient you can suggest, or that is one important question, that is Lennard-Jones potential. Remember a question for this year, second virial coefficient, discuss second virial coefficient and derive an expression for Lennard-Jones potential. So Lennard-Jones potential in terms shortly LJP. It is Lennard-Jones potential is a model made by Lennard and Jones. They are capable to study the features of interatomic and intermolecular interactions. We are considering interacting particles. Then for two isolated particles, they suggested, what is the assumption of this model? Lennard-Jones potential derivation, they suggested two isolated particles would not be interacting when they are infinite distance apart. That means if particles are very large distance apart, they cannot interact with each other. You cannot take interaction energy, even if you choose their Hamiltonian and Lagrangian, you cannot choose a interacting term, interacting energy for them. First assumption. The second one is the interaction will be attractive if the particles are at moderate distance. Or you can say Van der Waals type of interaction in which you have found. In Van der Waals type of interaction, it varies with sixth power of this one, sixth power of distance, or distance or intermolecular separation. And the third assumption is the interaction will be repulsive when molecules or particles are very close to each other. When particles are infinite distance, they do not interact. When they are attractive at a moderate distance, and they are repulsive when they are very close to each other. So this is the plot. It indicates how this plot indicates when they are very close, they are this portion, they are repulsive. This is the repulsive portion. This is the attractive portion. After that distance, here distance increases. This is the distance graph versus your attractive and repulsive energy. And when this further, when they are far away at infinite distance, the interaction is not taken into consideration. So the repulsive interaction and the interactive interaction, there is a calculated in terms of Lennard-Jones potential function in figure 12.1, that is phi r is minus c by 4 and r corresponds to 2 to the power 1 by 6. So you take the Lennard-Jones potential LJP, they suggested a function phi r can be some constant c into phi a minus phi r. Phi a stands for attractive, phi r stands for repulsive, and finally they arrive at the result phi r is equal to c n by sigma by r to the power 6 minus sigma by r to the power 12. So the equilibrium separation is here R0, and The fire takes the value in equation 12.31 C minus sigma by r to the power 6 and my plus sigma by r to the power 12, and the separation is 0 as the minimum value will also be equal to 0. Hence, we are capable to Lennard-Jones potential value in equation 12.32 as 4 epsilon 0 minus sigma by r to the power 6 plus sigma by r to the power 12. Using this, we calculate the second virial coefficient B2T in equation 12.33, where tau is k beta t by epsilon 2 pi by 3 sigma square sigma q tau to the power minus 1.4 this factor. Hence, you can calculate using Lennard-Jones potential. You can calculate the second virial coefficient, and the second virial coefficient divided by sigma square versus k beta t by epsilon 0 glass suggests there is a log scale temperature which varies in this manner. Then uh, then we can suggest from this expression, these are the conclusions can be derived from this graph. This is behavior of second virial coefficient. It agrees reasonably with the the behavior of argon, nitrogen, neon, methane and other gases. Typically, the value of epsilon 0 by k for methane and argon are 150 Kelvin and 120 Kelvin respectively, and the intermolecular distance of separation is 0.43 and 0.38 nanometer. The second, this figure conclusion, this Lennard-Jones potential suggests that the fire versus R graph at low temperature, the energy of the system is low. The value of the potential, Lennard-Jones potential, third conclusion regarding Lennard-Jones potential is much lower than 0. So second virial coefficient is negative, and this is possible in a low temperature. And fourth conclusion is at high temperature, the energies are high, and the effect of interacting forces, we can ignore the interacting forces. So the molecules behaves like hard spheres, and it tends to move positively, and the repulsive force becomes dominant. The fifth conclusion is at extremely high temperature, the hard sphere diameter ceases to increase with temperature, and at high energy, the molecules can approach more closely, accounting for there is a fall in the value of virial coefficient with B2, which depends on temperature. So initially B2T is negative, and finally it goes to positive side, passing through the value 0. You can find from this graph clearly indicates the how initially it was repulsive, then with increase in distance it passes through 0 at this point at a distance sigma, whose value is different for different gases, and this is this one. Hence, this is all about the statistical mechanics is purely dependent on quantum statistics. This is as well as it deals with some equations which are based on the quantum mechanical equations. Hence, we have studied the boson fermions various type of ensembles and their quantum behavior. We have focused on Bose-Einstein statistics, Fermi-Dirac statistics, and compared them. We have focused on Fermi energy and variation with their temperature. We have calculated certain specific heats and internal energy of the systems. We have depicted the behavior of fermions and bosons, and next as regards to their partition function and distribution function, next we studied interacting systems and how Lennard-Jones potential are able to explain the behavior of different interacting potentials. Let us close here. Today is the time to close. Tomorrow we will go through chapter 4. Okay. Thank you for your patience.
Thank you. Namaste, sir. Namaste, everyone.
Namaskar. Let us close today. Good night to all of you.
Very good night. Good night.